Assalamualaikum warahmatullahi wabarakatuh. My name is M. Said Jidanwalta from Numerical Method class. Over the past month in Numerical Method class, we were given a project task by our lecturer Padai to design and optimize a pressurized hydrogen storage with specific parameters. During our semester of studying numerical methods, we have only been exposed to theory and some applications and problems, but this time the task presented a realistic case where we needed to apply all that we have learned in numerical methods and other courses. It was important for me to be mindful and apply conscious effort during the process of this project. To me, what it meant by conscious effort means applying effort while being aware of my abilities, my limitations, and all the possible tools that could help my work from both the past and the present. It means being conscious of all the resources that I have available now and have obtained in past courses to select the right course of action, while being aware that there are some methods that are not feasible or those I have limited understanding of, therefore requiring consultation with experts or other resources. As part of my conscious effort, I needed to begin by understanding the problem that I was faced with. That is why I began with a case study of the parameters of the hydrogen storage that we were faced with. In my understanding, there were already many designs of hydrogen storage, even though they are on a larger scale. I can study from them and they generally take on a similar shape. Therefore, I should focus on the optimization process, which, my opinion, should focus on adjusting design parameters based on the requirements, which is 1 liter of hydrogen gas on 8 bars of pressure with a maximum cost of 500,000 rupiah. My study began on the properties of hydrogen itself, how much it weighs at those specific conditions and what kind of materials are suited to handle the substance at those conditions. The case study indicated that the hydrogen gas was nearly weightless at those conditions, and the selected material was stainless steel 316 after careful consideration over its availability, price, and mechanical properties over other choices, and in almost all cases, a cylindrical container design was most optimal. Following the case study, I continued with the design process, which comprises of several steps, which are determining the design variables, determining the objective function, and determining constraints. In order to optimize well, I needed to take from 3 different perspectives, each dependent on a variable and constraint, but they were all interconnected. The primary variable of the design was the geometry of the container, which comprises the radius and height. Based on my understanding, optimizing a known design would best be done by minimizing the resources required to manufacture it, meaning the geometry had to be material efficient, cost efficient, and fulfilling of the strength requirements. This resulted in 3 constraints, which are the geometry, the strength, and the cost. For the geometry, the objective was to minimize the surface area of material required to manufacture while keeping the same required volume, which is 1 liter or 1000 cubic centimeters. Using methods learned in Numerical Methods class, I decided to form a code that will numerically determine the radius and height by minimizing the surface area function. I was conscious of my limitations in directly making a precise code, therefore I broke down the code into 2 segments that will first find the coarse range of minimum surface area before the second will precisely determine the smallest radius and radius to height ratio for minimum surface area. In line with my conscious effort, I recalled in past courses that corners in typical cylinders serve as stress concentration regions, which are dangerous. Therefore, additional geometry needs to be implemented in the form of end caps that took 3 possible shapes: hemispherical, ellipsoidal, and toruspherical. Among the 3, toruspherical resulted in the least surface area, which is why I selected it, and designed it by filleting the ends of the cylinder, but I was conscious that this will slightly reduce the volume. Therefore, I needed to compensate somehow. By using an algebraic comparison, I formed a function to calculate that the volume actually increased slightly during the filleting process, and using the new volume with the code, I obtained the new radius and height values. With the geometrical constraint resolved, the next was the strength constraint. With some research, I found that the 2 main stresses experienced by these kind of containers are hoop and axial stresses. A simple formula can be obtained if we assume the container to be a thin wall vessel, where the thickness was maximum 1/5 of the radius. From literature, there were also a suggestion for the minimum thickness of such vessels, and with these additional constraints, I used a simple repeated iteration code to determine the maximum stress experienced at different thicknesses with the lower bound and upper bound based on the research that I did. However, all the thicknesses did not exceed the mechanical properties of the material I selected, meaning we need to select the thickness by the last constraint, which is the cost. I searched for data on prices of stainless steel 316. I assumed that the manufacturer of a small tin-walled container would be similar to the manufacturer of beverage containers, which were mainly by sheet metal forming, which means that I searched for SS316 metal sheet prices and selected a price range from a local distributor and took the price per unit area approach and simple iterations in Excel to test the prices of material required at different thicknesses that were sold by the manufacturer. Unfortunately, again, all the thicknesses did not exceed the maximum price of 500K, which meant that I needed to select arbitrarily. I selected the median 6mm thickness for balance and utilized a computer-aided design software to make a 3D model and applied simple simulation to test its strength. With the assumption that it is a thin-walled vessel, the pressure exerted at all parts of the inner wall is equal, and therefore a simple static test showed that no deformation is likely to occur, but the model was likely over-designed. In response to this, my final design used the minimum thickness of 3mm with the same properties and added a needle valve that I previously designed to highlight the container's functionality for storage and transport of hydrogen gas. From the process and the result of this project, it became clear to me how important and applicative consciousness is for facing our tasks and daily lives. My conscious effort included a step-by-step approach, understanding my abilities and limits, as well as recalling all knowledge that I have obtained in the past to tackle a present problem. Through this practice, I hope to face my days maintaining conscious effort in the face of all my problems and remain grateful for all my abilities and shortcomings. Thank you very much for your attention.